we will go to a new topic. That is what you guys asked me at the very beginning. How about the capacitor of the transistors, right? So let's look at this. First of all, we call it high frequency because this parasitic capacitor are very small, which is okay. Let's ignore it. No need to talk about this for now. But the main point is the MOSFET capacitor are very complicated. Let's first look at the cross section on the lower, right? I have NMOS here. We already learned the cross section earlier in the device section or EE128. So we have 4 terminals: source, gate, drain, which you know very well. Another is the body. We have been ignoring it. We don't talk about this much, but body is very important because if you remember, when we turn on the transistor, we are going to form a channel of electron here at saturation. Do you remember this one? And do you remember what is the meaning of this region that does not have electrons? What is that? What phenomenon is this? It causes channel length modulation, but from device physics, what do we call this? Remember? Pinch off. Yeah, very good. Pinch off, right? Because of pinch off, you have channel length modulation. Because at different VD, you have different amount of pinch off. As a result, your effective channel length is smaller, right? But anyway, this is the conductive plate. So this, of course, resides on a body, or we call it bulb or well, right? You cannot have a transistor, only have the gates, and you don't have the body. That is where your electron reside, right? So you actually have 4 terminals for each transistor. So what are the possible capacitors? Well, okay, I follow your approach. So he said that I have 6 terminals. So I have S to G, S to D, S to B, and then G to D, G to B, and then D to B, right? You just have 4 terminals. You just take the combination, right? Draw 2 of them without repeating. You have 6 possible transistors, but not all of them will have a big effect, and some of them does not make sense here. For example, X, S, and D, they are really far away, and this is not something we care about. And it's broken down. You can say as S to B and B to D. Remember, this is B because this is P, this is P, so this is just the body, okay? Same for G to B, we don't care because it is, actually we care a little bit, but not in but not in this class, okay? There can be some G to B. So in this class, it is small, we ignore, okay? So what are the possible transistors? I claim that this is one transistor, do you agree? I call it CSB. Okay. What type of capacitor? Sorry, I say transistor, I say capacitor, right? What type of capacitor is this? From E128. This is N, this is P. What type of capacitor is this? Why I have a capacitor between N and P? What do you call this? Is depletion region. And what is the name for the capacitor due to this depletion region? NP junction capacitor, right? I know you won't remember the name, yeah, because they even don't test you, right? They test you how to calculate, but they don't test you what the name it is. It's the junction capacitor, right? So similarly, I have another junction capacitor between D and B. Make sense? Because there's a NPN junction. Now, the drawing is not good. This is the gate. Between the gate and the channel, I have a capacitor. Do you agree? And here you tell me that it is the depletion layer forming the insulating layer, right? For the junction. What is the insulating layer for this capacitor? the oxide, just the gate oxide. It's insulator, right? I have a conductive metal on the gates and then a conductive inversion layer full of electrons. So there is a capacitor. Do you think this is going to be a big or small capacitor based on the drawing? Big. Why? Because it's large. Yeah? Capacitor depends on area, right? And also the insulator thickness, right? From insulator thickness, we really don't know, but usually this is much thinner than the depletion, but also depends. But anyway, it is large. We do need to have a large transistor. Now, then naturally you will also say, how about here? Because I didn't have an overlap, I have N here and then here, right? So I forgot to tell the name. How would you call this capacitor on the left? C what? Yes, C ox, good. But in this analysis, we will call it is proportional to C ox. But in this analysis, we just call it CGS. I know I know very naturally you think this is B, right? But because B is P-type, this is N-type, so it kind of disconnected from B. But this is connected to source because they are all electron, right? So that is CGS. How will you call this then? CGD. Do you think CGD is small or large? Should be small, right? Because I only have this overlap. Yeah, but it turned out to be very, yeah. Correct. Because here is disconnected. This is depletion, right? It's just like insulator. So this will be a gate, and then this is the source, because this is electrically connected to the source, right? CGD is much smaller than CGS because of the area. And we try not to have CGD, but there's always some fringing field or overlap. But they are very important because of Mueller effect. They are small, but we always, for common source, you are going to amplify this like what we saw earlier, okay? But anyway, my goal here is to tell you that there are 4 capacitors: CGS, CGD, CSB, and CDB, right? And you told me there were 6, and I just told you that because CSD is far away and also is decomposed into the other capacitor, right? CGB, we don't care that much. It's really, really tiny. So we ignore, okay? Now, how about for PMOS? Well, we put in N well, is the well, but however, this is again the body because this is N and N. And then you have this source. So you have the same situation. Okay, maybe you can try to draw it yourself. If you don't know, let me know, right? Now, but however, you see that when I discuss the capacitor, I need to draw the geometry. Then it means that at different operation region, I have different capacitors. For example, when it is in linear mode, this one extends all the way to the drain, right? Then actually for modeling purpose, we will have CGS and CGD the same. We just give half to the CGS, half to the CGD. That's for modeling purpose. And just, you don't need to know, but because just now you said that CGS might be equal to COX, but you see that based on this, it is not COX because it's not uniform distributed and it's not all the way. Indeed, a good modeling is 2/3 of COX. 2/3 of COX. 2 divided by 3 times COX equal to CGS when it is in saturation. And how about in the off state? Off state, there is nothing here, right? You only have CGB. You only have very tiny CGS because there's no conductive plate. This is purely P-type. You have CGB. Now CGB becomes important. Okay? So the only way I want to tell you that is it's very complicated. For example, if you take EE224, the digital circuit, we will analyze all these regions because this is going to determine the delay of your inverter. The inverter go through off state, linear mode, and saturation mode in the whole transition, right? So we need to analyze that. But anyway, yeah.
So they make a really good transistor. Not CSD, but if there's very small 10 population, then that includes CSD. Because you're electrically.
No, I mean, first of all, I think you are trying to say that the gap is very small, right? So this has nothing to do with the whether I make it good or bad, because I just make D very small, then it will just touch, right? But when it is just touching, then it becomes linear mode, right? It's just two conductive plates. Then I can just partition that. Remember, this is modeling. When you go to this regime, it becomes meaningless to distinguish in this way. You need to solve the Maxwell equation to get the overall response. You can say they are coupled. So in modeling is that we look at the situation we work on, for example, saturation. And then we know there's a clear separation between the drain and the channel. And then we model in this way, it can predict the result. But for those boundary case you're talking about, it becomes not that meaningful. Sometimes the model may break down, right? Not everything can be modeled completely by RC network. Otherwise, we don't need Maxwell equation, right? Yeah. So that is a good question. Yeah. Okay. So for capacitor, any questions? Now, if no, then let me redraw the capacitor one more time. This is, can you tell me what is this? It's in the midterm. CSB. What is this? CDB. And then I will still draw this. How about this one? CSG or CGS, right? Sometimes I swap it. What is this? CGD. Okay. We are not going to draw this cross section every time, right? We are circuit engineer. We are not device. So because of this, we will go back to our transistor symbol. This is MOS. Now in the past, that's it. I say this is gate, this is drain, and this is source. But now in order to include the body, in reality, right, I think you sometimes also see this type of connection, this type of symbol, right? But we don't draw it, right, in this class. But if you later in the lab 8, you are going to use a real technology, cadence simulator. Then you need to hook up the B. Okay? Now, so we have 4 terminals, right? Which makes sense. So I have CGD. I'm going to call it CGS, although there's nothing wrong to call it CSG. And then I have CDB and CSB. That's the 4 transistor. Okay, that is the symbol. Now, how about in small signal? You just repeat what you learned before. Just do the small signal first. I have a gate. I have the GM, VGS. I have RO, right? That's it. But then now it's time to fill up the capacitor. What do you call this? CGS, very good. How about this? CGD, right? And then how about the other 2 capacitor? Very good. Then someone say to ground, but hold on. CSB. The problem is I never show you B in the small signal model. If you go to more advanced class, you do have the B, you have the GMB. You also have the transconductance. But in this class, that's okay. Let's just put it to ground. That is exactly what we want to do. So in this class, in EE 124, we always assume B is grounded, right? We need to ground it, right? But this is not always the case. Think about, it depends on your layout. If you have a common source with degeneration, you have the rights to ground this to make the body to ground or connect the body to the source. Then your body is not grounded, right? So really depends. But in this class, let's just do this. So similarly, I also have another capacitor CDB. I again assume it is grounded, right? So while here I did not draw that it is grounded, now I will say that this is grounded. Okay, so this is the green triangle and the green triangle. Is this okay? Okay. And now my question for you is, why we only study this at high frequency? Right? Why I did not add this when I did the common source amplifier analysis earlier? Very good. Because they are small. They are small. But small, of course, is relative. Impedance equals to what? 1 over omega C. So when they are small, if you have a low frequency, then this tends to infinity. You have a small omega, you also have a small C, then it becomes infinity. Then they are just open circuit, right? I don't care. But at high frequency, now the omega becomes large, right? Then this one has effect. Right? You start feeling the effect, right? If your omega is really high, then becomes almost shorter, right? Of course, it's a big impact to a circuit you need to consider. And when they have impact, it means you have roll off in the gain, right? Any questions? Okay, if no, done. It's easy. We can do the exercise. For this setup, we first want to identify all the capacitor and then simplify it. Now, this all based on what you learned before. You cannot rush. Do it step by step. First, what are the transistors that we have? Bottom is NMOS or PMOS? The bottom one, NMOS. The top one, PMOS. And because of this is source, this is drain, this is gate. And what is this? Also drain, this is gate, this is source, right? Because PMOS has the higher potential at the source, right? So I've been very careful doing step by step, right? That's why it's important to identify the source. Otherwise, you're going to label it wrong, the capacitor, and then you will check the equation. Then you think it's 2 divided by 3 C-ops, but it is not, right? Okay, good. Then I start drawing the capacitor. How many capacitors should I have? 8, because I have 2 transistors. Very good. So I will start. What do you call this? CGS. I'm going to call it 1 because now I have 2 transistors. How about this capacitor? CGD1. And then I know that, although I don't see it, but I know that I must have CSB1, right? Very good. And then from here, they're just the same 9. I know that this is CDB1. Okay, I'm done with NMOS. Then let's go to PMOS. What do I have for PMOS? What do you call this? CGD2, thank you. And I just go through my cheat sheet. I know there are 4. This is CGS2, right? I cannot make mistake, right? And this is CSB2. And again, the same terminal I have. What do you call this? CDB2. And although I did not do it, this of course is grounded, VDD. So I have 8 capacitor, but some of them are useless or have no effect. For example, is it important to include CSB1 in this case? It is grounded at both terminals. This is ground, this is ground. It means no matter what happened to your transistor, I have 0 potential or a constant potential across my capacitor. That means I'm not going to draw any current. If I'm not going to draw any current, it means as if I'm not there, right? You invite many friends to your party, but they just don't eat. You don't need to count them when you order the food. As simple as this, right? So this one can be gone. Can you spot another capacitor that can be gone also? CGD2. Why? Because it's short. That means this terminal and this terminal all at the same potential, right? So again, it's not going to draw any current in the whole operation. It's not intuitive. You may feel uncomfortable. You feel that maybe there's something, but indeed, just think carefully. They all at the same, always at the same potential. So I now only have 8 capacitors. And then some of them I can combine, right? What I just done is elimination. What can I combine? I will combine those have the same terminal, right? Do you see that this one connected to this node and to ground, this connected to this node and to ground, they are just parallel to each other. So I can combine them as CDB1 plus CDB2, right? How about this one? This is grounded at the source, right? So I cannot combine. But most tricky one is this one, difficult to see. I claim that I can combine this with this. Do you agree? I can combine CGS2 with CDB2 or CDB1. Do you see that? Just look at the terminal. Both of them have that connected to D. Yeah, this is G, but this is shorter, right? So this is D. And this connected to VDD, but VDD is grounded, right? So I can make this into something like this. Now it becomes simpler. I have this. I have still here. Sorry, there's one more I can eliminate. I did not say that, right? Thank you. CSB. Yeah. So I eliminate 3, right? Now only have 5. But then I combine this 3 to here. I call it CGS2 plus CDB2 plus CDB1, because in parallel, I just add them together, right? So I get rid 3 and then I combine 3, I still have 2, right? Which 2? CGS1 and then this one, CGD1, okay? So you are almost there. You can even call this, I don't call this, maybe I call this C out dash, maybe. Okay, call this C out. I only have 3 capacitors now. Can I further simplify? Well, not really, but if I ask you to find the pole, then you will complain. You say, almost there, but there's capacitor giving me the trouble. Which capacitor? CGD1, right? And what will you do? Use Mueller theorem. Very good. Right, so this is 1, 2, and then finally use Mueller theorem. I'm going to break CGD1 to CGD1 times 1 plus, or let me just use the original equation, 1 minus A at the input, and CGD times 1 minus 1 over A, right? Let me give it a name so that I call this CGD1 in, CGD1 out. Okay, then what happened? I'm going to cross this out, and this one becomes CGS plus CGD1 in, and this one becomes CO plus CGD1 out. Is this okay? Right. So this is like, we go back. So yes, I have a capacitor. If you try to solve KCL, KVL, it's really a nightmare, right? Even with 2 capacitors, it's a nightmare. But now by using all this and then with the inspection method, I can find the pole of this common source amplifier easily. I can estimate. Okay. Any questions? So then, so this is what you will see in the in your homework. You have